Hello all. I want to talk about Eta, the newest entrant to the programming languages which run on top of Java Virtual Machine. Eta is a purely functional, lazy, and static type language. Each of these attributes bring in a lot to the table. They add a lot to your application development. They make your life much more simpler, and they make software development experience much more easier for you. So the primary goals of the Eta language are mainly cross-language interoperability and concurrency. I'm going to elaborate slightly on each of these topics. So the Java virtual machine already hosts a lot of languages. For example, in this diagram, I'm just demonstrating 4 of them like Scala, Java, Clojure, Kotlin. But there are also a lot of other languages. They have developed over the time and they have their own ecosystem. They have their own niches in which they are good. Scala already has systems like Spark written on top of it, an actor model like Akka written on top of it. Clojure has Torn, Java has a lot of enterprise-driven software written in it, Kotlin is being used in Android. So when we bring a new language to the ecosystem, we don't want to start everything from scratch. And as you can see, all of these languages do have some amount of foreign function interfacing, interoperability between them. First of all, they are not type safe. Secondly, they are not smooth. Foreign function interface in Java was there for a long time. Java has JNI, but it has traditionally not been a really smooth experience for developers. So one of the primary aspects that we target is foreign function interface. So this is something we call bidirectional FFI. I'll go into a little bit detail of why we call it bidirectional, but the main thing to understand is that FFI should be a first-class construct. When you are hosted on something like the Java virtual machine, which already has so many languages, so many ecosystem developed on top of that, you cannot afford to be too much opinionated when you are working on a particular set of problem, because the problem has various aspects. And suppose tomorrow you are doing Android development, you want to use some small API, something which was well developed, maybe in Kotlin, and you don't want tomorrow that your whole company, the whole organization has to migrate to start using Kotlin and understand that. The process has to be really smooth, and FFI enables that. And we actually do have an automated tool known as Eta FFI. So if you feed it any jar, so as we know, all jars run on top of the JVM. So if you feed a jar written in Scala, a jar written in Clojure, a jar written in Kotlin, the Eta FFI actually emits the foreign function import code of Eta. So you don't really have to worry about writing wrappers or anything like that. So if a system like something popular, like say Elasticsearch is written in Java, you will see that all of these languages are developing their own wrappers. In Eta, once you feed the same jar to the Eta FFI tool, it generates the FFI import code for you. It generates all the boilerplate and it takes care of all that. And you don't have to worry. It's just like using a simple another jar, another library in the system. So Eta, the reason why I made it sit on top of that is because cross-language interoperability is one of the primary concerns in here. So we actually have written bindings for Spark, which is written in Scala. We have written bindings for Storm, which is written in Clojure. We have lots of libraries written in Java which are interfacing with Eta, and they are really, really smooth. One of the also major benefits which we are targeting and why we are calling it bidirectional is that Eta is a dialect of Haskell. Haskell has traditionally been used in a lot of high performance applications. There are a certain niche of applications in which Haskell really performs very well. For example, when you are writing DSLs, Haskell has the best parser combinator libraries in the world, no doubt about that. And in an imperative language like say Java, you want access to the amazing libraries, or some amazing parser combinator libraries and some interfaces to that. So till now you didn't have the access to that. But Eta being a dialect of Haskell, you have access to the entire library system, the entire frameworks, all the frameworks that exist in Haskell, and you can import all of that. And you can import all of that in Eta, and then when you export the Eta code and export it to the Java side, it becomes really simple for them to use it. So cross-language interoperability was one of our prime concerns, and we try to make it a first-class citizen. So that is something I'm going to demonstrate in this talk and show you some examples of using Spark and how it's really, really smooth when you're working with Eta. The second thing that we work on, or the second goal or objective, as you can say, of Eta is concurrency. So concurrency, the end of Moore's law, has really led to a rise of functional programming. We see that Java 8 has also accepted Lambda. Java 8 came up with Lambdas. We see, I think I saw a proposal of language of bringing some other features like pattern matching, etc. But the main thing is that concurrency is really an issue, and we primarily have developed a lot. The team of Eta have worked a lot with object-oriented systems, and we thought that the basic fault in object-oriented system, when you're working in a concurrent setting, is that objects tend to hide the wrong things. So encapsulation is a very important concept in software development in general. Encapsulation is really important, but objects encapsulate the wrong things, which I mentioned over here. So as you can see, objects encapsulate state, and objects also encapsulate sharing. So whenever you see a program in Java, C++, or any other object-oriented language, you can never say by looking at an object what state is hiding behind it and what kind of references it is sharing, if it's sharing some pointers. You cannot predict anything like that. And that sharing and the hiding of sharing and state has a name that is called data race. So in object-oriented languages, in a concurrent setting, you get data races for free. So the fundamental approach in pure functional programming is different. Pure functional programming has immutability. It doesn't allow mutation. It doesn't allow you to change the state. And it also works instead of sharing. So whenever you talk to any other pointers or reference, instead of sharing, you actually do copying. So people would generally tend to complain that copying has to be slow. Well, it is. But it so happens that the runtimes have really powerful garbage collection nowadays, and it uses some fundamental different structures known as persistent data structures, which makes it a lot more simpler to deal with. So as a result, you do not have any data races. So object-oriented programs do have a lot of concurrent software has been written in object-oriented program, but the basis of that is locks, and locks do not compose. So composition, I feel, while functional programmers say that functional programming in the composition is the basis of functional programming, I feel that composition is the basis of software engineering. We are taught this from when we start development, that you always do not tackle the entire problem. You break it into pieces, and when you solve one piece of problem, you want to compose it, bring it together, and make sure that it works. And that's how you build a system, by composing small blocks of system. But locks, which is the solution of object-oriented programming languages to concurrency, do not compose. So pure functions gives us a lot more advantages. It gives us a lot more APIs. And I'm going to talk about something known as transactional memory. So we are going to give a demonstration of the Dunning philosopher problem solved using transactional memory. We might give a few more examples showing some practical examples of why transactional memory is a much more simpler API and how pure function enables software transactional memory. Transactional memory is a very simple concept. It's just the concepts of databases like atomicity, consistency, and isolation. Just taking those concepts and bringing it to our application and making the threads obey those laws. And when we do that, our transactional memory primarily composes, and it makes application development under a concurrent setting much more easier. You don't have to put in much more thought to your development. Your software is not very difficult. It's not very different from the normal single-threaded, and you get free speedups. So that is another thing which Eta brings onto the table, that it has a very good transactional memory implementation in its runtime, and that is another thing which we are targeting. Apart from that, we have some rather esoteric features which people don't deal with everyday life. So we have something called as dependent typing. So suppose you are multiplying a 2x3 matrix with a 2x1 matrix. When you are multiplying this is not possible, right? But when do you encounter these errors? You always encounter these errors in your runtime. And in a large application, there's going to be a lot of systems like that. For example, you're dealing with a vector or a list, and you try to extract the first element of it, and that's an empty list. That throws a runtime error. You can encode these rules in Eta. The Eta type system is so powerful, it understands dependent typing. Is the basis of dependent typing is that you can put in a lot more rules onto the compiler. The compilation time, the build time increases as a result of that, definitely, but that makes your software a lot more safe. That is dependent typing, and we are going to demonstrate with an example of how dependent typing makes software development a lot more easier. We are going to use a very small example, but also another esoteric feature which we will talk about is something known as linear types. So in high frequency trading on applications which have really low latency, people don't want to deal with garbage collection all the time. Garbage collection for most of the 99% of our application, or I would say 95% of our application, garbage collection is really fun. You don't want the application programmer to worry about how memory is managed. But again, there are certain classes of application, the example which I'm giving is high frequency trading, and certain classes of other problems also where you do not want garbage collection. The developer himself is aware of how memory allocation is going on, and he wants to take charge of controlling the memory. That is not an easy task. Developers in Java don't do that. I've very rarely seen code which actually does that. A very niche quantity of softwares actually use that fact. But linear types help you in that. So linear types is something similar to a concept which we actually are familiar with in Rust. So Rust has this concept of affine types, which the linear types is almost a similar concept, that every object, every pointer has its own ownership, and when an object does an amount of memory allocation, we can actually track that. And the type system enforces you to free that. So if you don't go ahead and free it, you are not going to be able to be compiled. So imagine that malloc and free is enforced by the compiler. That's a really powerful feature, and Eta is bringing that onto the table. Apart from that, there are a lot of other features. For example, I want to talk about type-safe distributed systems, where I'm going to demonstrate a small example. Some things which are not actually possible in Haskell, which actually is a really good advantage of object-oriented languages like Java, which has reflection. So when you are actually transmitting a function or say a closure, you cannot capture the type information about the free variables, but the Eta type system allows you to do that because it has access to the reflection mechanism in Java virtual machine. So that makes distributed systems a lot more easier. So when you are sending a closure or a function, you can actually encode the type information at runtime and make sure that it's much more safer. So I'm going to demonstrate with a small example on this. Also, some other things we'll be talking about is streaming and fusion. We are going to talk about quick check. Quick check is something which has which was originally developed in Haskell, but it is catching on in a lot of other software. I've seen Clojure now starting to use Clojure spec, and which is basically a way of telling your specifications, and you don't manually have to write tests. So we get that for free in Eta because Haskell already has the quick check library, and quick check makes sure that you just write your specification of what you want your function to do, and it will auto-generate tests for you. So that's really a powerful feature. And also in streaming kind of scenarios, it's really fast. So for example, say you are dealing with a data pipeline which actually has a function, say f1 applied to it, followed by that a function f2, followed by that a function f3, fn. So n number of functions are being applied to data. So as you can understand, at every step, an intermediate garbage value is generated, and that value is fed to f2, that is fed to f3. So this kind of system is very common in streaming systems where you build a lot of pipelines and you actually apply functions to it. But the intermediate garbage that is generated is not necessary. So because it's a pure functional language, Eta, the compiler does a lot of optimization, and one of the most coolest optimization that it does is something known as fusion. So when it sees that a series of pure functions are chained together, what it can do is actually it will allow you to fuse those functions. So what it will do is f1, f2, f3, fn is going to compose all of that function and going to give you a single function called h. And you can apply that function, just that function to your, instead of making your data pass through f1, f2, f3 individually, you can apply the whole entire composed or fused function to your data, and that makes life really simple for you. That generates a lot less garbage, and that's a really powerful thing to have when you're dealing with streaming systems. And we are actually going to show you benchmarks in this talk where I compare Akka streams with the streaming package in Haskell, which we put in our Eta setting, and we actually run a benchmark and show that it is much more faster than Akka streams. So this and a lot more examples of how functional programming and the type system really makes your life simple and helps you write much more correct software. I hope you all come to it.
Thank you.